Hello, everyone. Welcome back to this to this session here for security testing and continuous vulnerability assessment of Cyber Science 2020. Our third speaker for this session is Drew Malzahn from the Johns Hopkins Applied Physics Lab. He's presenting us a paper titled Automated Vulnerability Testing via Executable Attack Graphs. So, Drew, thanks for joining us today. You have approximately 20 minutes for presentation, more or less, so that we leave enough time for questions at the end, should we have any. Right?
Great.
Over to you. Thanks.
Thank you. Yeah, so very quickly, thank you to Cyril and all the other conference organizers for allowing us to present. Also, thank you to my co-author, Zach, who's also on the call, for just being generally awesome. Like was said, my name is Drew Malzahn. I'm a cybersecurity engineer at the Johns Hopkins University Applied Physics Lab. And a while back, we had an internal research and development project that was focused on a couple key problems in cybersecurity. So namely related to cybersecurity risk. So cybersecurity risk is obviously extremely important. And normally when you think of modeling and cybersecurity together, the first thing that most people think of is some sort of risk model, because it's extremely important to the business decision-making process. The problem with cybersecurity risk is that it's generally generated by risk assessments, right? And risk assessments are mostly human-driven. They're not generally reproducible or consistent. And of course, that doesn't mean they're bad or that they're not useful. They're of course very useful, but comparing two different risk assessments done in different ways by different people isn't always possible because they're not very scientific. They're not data-driven. They rely heavily on historical data. They rely on expert opinions or arbitrary grading scales. And we would really like them to be more scientific and more repeatable, because that builds a higher confidence risk assessment. So again, it's not like the results are bad, but if you could verify the results by repeating the risk assessment, that would be better. So one possible solution for getting this sort of reproducibility and data-driven assessment is using attack graphs. So attack graphs are a set of logical dependencies that described the movements of an attacker or the capabilities of an attacker within context of some network, right? So talking about vulnerabilities in this way, instead of just as the output of some vulnerability scanner or standalone things, facilitates two things, which is automation and formal analysis. So theoretically, if we do an attack graph-based analysis with some automated tool, when we run that analysis again with the same parameters, we should be able to verify results and come up with a higher confidence that we did get the right results in doing so. And so again, this all sounds great. This is something that's not meant to replace risk assessments. It's more like a complement, an additional piece to that kind of holistic, more process-driven risk assessment. So the goal of this paper, AVRA, it has a couple of high-level goals. AVRA stands again for Automated Vulnerability and Risk Assessment Methodology. And our goal with this project was two things. Firstly, to create better tools for automatically generating these attack graphs and have it be really convenient and easy to generate very semantically rich and interesting attack graphs with large networks. And in doing so, increase confidence in risk analysis as a whole by doing automated processing on these attack graphs, and specifically with a focus on verification of the attack graph. So how do we know that what's in the attack graph, the things that the attack graph says, are actually true? And how can we verify those results by reproducibility and consistency? So the tool or the methodology is composed of three different parts, which you can think of as like a pipeline, right? So the first stage of the pipeline here is the system scanner, which basically is just an aggregator of information. We take a target network, you could think of it like a real enterprise network, and we get host information, we get information about the network topology, operating systems, running processes, all these things, and comprise that into what we generally refer to as a system model. So it's not an exact representation of that system, but a abstract representation that tells us the things we're going to need to know to make that attack graph. In the second stage of the pipeline, we have our attack graph generator, which is where, of course, we create the logical attack graphs. Again, these can be thought of as a set of logical dependencies that the attacker needs to reach some sort of goal. So that might state something like, this machine is vulnerable, and the attacker has this password, and he knows how to log in as this other user. So given those things, the attacker has user privileges on this host. And again, the goal here, I want to emphasize this, is that we are trying to structure and formalize a lot of this reasoning, because it allows us to do things like put vulnerabilities in context with each other and drive towards reproducibility and more data-driven assessment. So finally, in the last stage, and this is the most interesting part, we want to verify that the results of our automated analysis are actually true. So you have this attack graph, it says you're vulnerable or you're safe. Especially for the vulnerable portion, we're very interested in trying to make sure that that's real, that's a reflection of reality, that our abstract model reflects reality. So how do we do this? And the way we came up with that is by actually implementing a proof of concept. So what the final stage of the pipeline does, this is the fun part, is actually walk through the attack graph and look at all of the nodes and try to satisfy those logical dependencies and actually launch exploits against the network. So the idea is, we know if we can exploit our own network using this abstract system model, then the system model is representative of the reality that your network is vulnerable. And that's a really hard and interesting problem, and we'll talk more about how that works. So this is a high-level overview of everything I just said, kind of summarizing the things on the last slide. The only plug I'll make here is it demonstrates the pipeline really well, and you'll also notice that these components are all very separated, right? So like we have our vulnerability database, we have a source of vulnerability data, we have this auto exploit tool. All of those components are pretty pluggable, and as long as they feed into each other in a consistent way, you can use your own database, you can use SQL, Postgres, whatever. If you have some sort of first-party source of vulnerability information, it should be easy to modify and use that too. Okay, so getting into the meat of how these things actually work. The scanner right now is an agent-based tool for collecting the information that we want to put in the system model. And the scanner is very important because it's the first line of defense, you could say, in making something the difference between a research concept and a useful tool. And again, we want going back to the first goal, we want this to be a really easy way to generate and analyze attack graphs. So we need it to be something that's operational. And how we did this is mostly centered around a tool called OSQuery. OSQuery is a system monitoring tool developed by Facebook, actually, that captures system state of structured data and presents it as SQL tables. So on top of this, the core of this agent is OSQuery, which is doing that collection. Then we have some custom code that's processing that information and pumping it out and putting it into our database of choice, which is MongoDB. So the scanner, again, it's a very important contribution. It's something that's absolutely needed to make the tool operational. And in the literature that we've previously seen regarding attack graph generation, even automated attack graph generation, the scanners are either more or less abstracted or not super well addressed. So we thought it was very important to emphasize that. So onto the second stage of our pipeline, we have the graph generation. And starting at this point, we have our idea of a system model. So we have this abstract representation of the system. how do we turn that into an attack graph? In keeping with the theme of being operational, we're wrapping another tool from attack graph research called Molval. Molval is a logic-based security analysis tool specifically designed to create attack graphs from a model specification. So that model specification is written in Datalog, which is a subset of the logic programming language Prolog. So we're going to talk a little bit about Datalog and how that executes and how it arrives to answers. The first thing is starting with the system model and coding it as rules and facts, right? So essentially within a logic programming language, you have some sort of initial system state, right? And you have rules to get to new states. So these first thing we need are the rules. The rules in this context basically describe what the attacker can and can't do with the information and resources that they have accessible to them. It's how the system behaves as a whole, though, generally. At this stage, we're manually developing those, and we'll talk more about that later. Next, we automatically generate facts, which again, the rules get applied to facts to create new facts. So you can think of these things as statements about what is true about the system, right? What is the initial state, and then what new states can we get to? The key question here, though, and the really hard research problem is how much abstraction is too much? So we could describe some very specific models of how certain things get exploited, and you know, how a specific process on Linux works or something like that. But do we want to do that? Is that useful? Can we get away with doing something that's easier to describe? And there's a lot of opinions on this. There's a lot of different previous literature. So we just decided that we were going to come up with our own rule set and focus on really getting that automation piece down. So again, there's other kinds of rule sets that you could make, but we want to design one specifically for automation. And right now that means we focus on remote exploits and also privilege escalation exploits, generally on Linux systems. And the structure of this again goes, you have a rules file that says something kind of like hosts are vulnerable processes. Hosts with vulnerable processes are vulnerable themselves, a logical implication. And then you have a facts file that says, here's the state of the system. This host has this set of processes running on it. It's affected by these vulnerabilities. And then Molval does the work of stitching those things together and coming up with the conclusion that host B is vulnerable. And why? Because this, this, and this. So here's a more in-depth example of that rule and what it looks like. If you're familiar with Prolog or Datalog, then this is basically just a Prolog program. But if you're not familiar, what this is actually saying is that the part in red is true if the body is true, which is the part in green. So if we have all of these different facts and rules that we can logically say are true. So if there's a vulnerability on this certain host and the host is listening for external connections and then we can logically state that the attacker can compromise that host. So once all of those rules kind of come together, you have the attack graph itself, and here's an example of that. This example was generated from an extremely small network with a very specific vulnerability on it, and it has 40 nodes already, so that kind of gives you an idea of how the scaling works. And again, this is demonstrating a remote code execution vulnerability, I believe. Okay, so now that we have that graph, so now that we have that graph, which is essentially a proof or a trace of that program that's executing inside of Molval, basically saying we know the host system is vulnerable. Why? Because this is true. Well, why do we know that? Because this is true, and so on. We can walk down that dependency graph and try to actually launch the exploit. So surprise, surprise, we're wrapping another tool. This one is Metasploit, which you're almost certainly familiar with. It's a penetration testing framework from Rapid7. And Metasploit handles a lot of things really, really nicely. It handles payload setup. It handles actually launching, sending the cybersecurity attack, the exploit, and it also handles session management. So keeping track of who you've exploited and who you haven't. And a little known feature, it actually provides a RPC daemon so that you can easily interact with it through other programs. All of that made it a really good candidate for our auto exploit tool. The process here again is we ingest the attack graph, we walk down the different paths in the graph, we look at every node, we try to decide if it's true and if that's part of a cybersecurity attack. And if it is, then we actually try to execute that attack. And if we're successful, then that means that the attack graph is correct. If we're not successful, that means we need to go back to the drawing board. Okay, so there were a lot of challenges generally in building this tool and also in future work. So we'd like to talk about that briefly. These can kind of be divided roughly into more engineering challenges, like something isn't built yet and we just need to actually build it. And also like very conceptual hard challenges. So what are those challenges? Starting with the scanner, of course, because it's first. This kind of drove home while we were building this, how difficult finding a vulnerability is by itself. Just the task of deciding what is a vulnerability, where is that vulnerability present? Like, is it the fault of the software? Is it the fault of the architecture? So on and so forth is hard. It's a hard challenge. And one of the reasons that this is hard is because operating systems are not designed for compact, explicit, automated representation. So if you think about the amount of metadata that's on your computer about the computer's operating system itself, short of like scanning kernel structures and stuff, it's actually pretty little. You might have a package manager in Linux, you might have the registry in Windows, so some other structured data stores, but besides that, that's just not what operating systems are designed to do. So we'd be interested in future work in seeing how that would actually come into play. Could you design an operating system that's has the goal of being a working operating system, but also has the goal of facilitating automated reasoning about itself? So in the graph generation stage, automated rule generation is obviously the golden goose here, right? So I said before, rules are developed by hand and that there's many rule sets and that it's not necessarily, we're not necessarily sure which one is the best one. So right now we can change out rule sets if we want to do a different kind of analysis. But what we would really like to do in the future is use some sort of automated technique to generate those rules. And that could be structured fuzzing, that could be some sort of static analysis, that could be some mutation on existing exploits to try to make them work with other things. There's a lot of different directions that could go. And of course, from a more modeling abstract perspective, representing the effects of an attack itself is hard. That's something we're currently working on right now, actually. But that's even hard with known attacks. The really hard problem is representing zero-day attacks. Like, how do you conceptually reason about something that we don't yet know what it is or how it works? Not sure we'll ever even get to an answer on that, but it's an interesting direction of research. With the auto exploit tool, the obvious improvements and comments would be with the success of the exploits, as that's what it's designed to do. So the interesting research for us here is not necessarily designing these super crazy cyber attacks, but grading the quality of what we have. So it's kind of an unknown problem, an open problem, like how successful is Metasploit? How successful is it versus other kinds of penetration testing frameworks like CrowdStrike? How would we determine the success? How do we increase the number of exploitable systems broadly? So on and so forth. So I will say, even though we don't know, there's no way to tell how good Metasploit is because we don't even really yet understand what good means, like probability of success, how quiet it is, how fast it is, like what is your metric. But we will say, and we note this in the paper, that of the things that are usable in Metasploit, 67% of them are usable right now by Avro with no additional configuration. So using some very simple heuristics and fitting in the information we get from the attack graphs, we can launch more than half of the exploits in the exploit DB and do that automated reasoning. So that's really nice to see. So those are a lot of hard problems, right? But we're not going to tackle all of them just by ourselves. The future work that we're most directly interested in is, in the immediate term, is expanding the rule set to reason about more attacks, increasing the success rate of the auto exploit tool, looking for supports for more kind of systems, walking through the graph more efficiently. That's something I forgot to talk about in the last slide, but picking a path based off of different metrics. So there might be multiple ways in the graph to attack a network, but which one do we choose? And then finally, kind of flipping it more to the blue team side, doing analysis on the structure of the graph itself to recommend mitigations. So we might do this with some sort of cut set analysis. We might do it with logical inversion and then regenerating another kind of graph. But yeah, we're excited about working on that. And I think that's it. So if anybody has any questions, I'll be happy to take them. Thank you for tuning in.
Thanks, you. We have some questions here. So does your scanner consider if the target system has a honeypot on a net?
On a what on a net? Sorry, could you repeat that?
Does your scanner consider if the target system has a honeypot on a net?
A honeypot? No. So the scanner really only looks at that stage at the operating system itself, right? So it's a program that you install and you use it to collect the information. So the scanner doesn't necessarily know, oh, this is an FTP server running in the DMZ. It just knows that, hey, we're talking about Linux and it has these processes running on it. And one of those happens to be listening on port 21 and 22, or yeah. So that's probably an FTP server. That is something we have discussed though, adding in this concept of sort of a mission-based model. So the purpose of this section of the network is to do this specific thing, or this machine is a honeypot, and this machine is an email server, and this machine is this, and analyzing how that might change the attack graph. I think that would be most helpful in the auto exploit tool area for that path prioritization piece that we talked about, right? So trying to decide what are the high value targets and what are the easiest ways to get there.
Okay, then we have a second question, which is, will AVRA be available for researchers to use?
So we are continuing to develop it internally. I wouldn't necessarily say no, never, but right now we're not thinking about releasing the source code publicly yet.
Okay, super. I think we have exhausted all the questions that we got. So thanks again for your presentation and for joining us today. After this session, we are going to take an hour break, and we'll be back with our last keynote speech at 3 p.m. UK time. So see you in an hour and a bit. Thanks.
Thank you.
Bye-bye.